3, according to this. So the chapter will probably be different, but we're going to look at something called the p-n junction. We're going to learn a little bit about semiconductors. Let me pause it. So we'll look at something called doping. We'll look at N-material, P-material, something called depletion region, barrier voltage, forward bias, reverse bias. Use the term, it's very important. Forward operating current, something called peak inverse breakover voltage. Then how to test these devices called diodes. So the doping is the process of adding either trivalent. Y'all know what valence is, right? Y'all know the way an atom. So how's an atom made up? What's the parts of an atom? Now we have one unit. We have two major parts. We have what we call the nucleus, and then we have electrons that orbit around the nucleus. The nucleus consists of protons and neutrons. And what's the difference between a proton and a neutron? Well, not a proton and neutron, you're close, but the proton is positive and a neutron is neutral, which means what? It has no charge. Your electrons is what has the negative charge. And of course, we know that positive and negatives attract each other, and this is what keeps these electrons in our orbits around the nucleus. And if you ever had chemistry or anything like that, or any biology classes, you learned that the atom is made up of shells. Usually do out of Boyle's model, I think, is where they draw it laid out, where the orbits are not really perfectly around the Earth. You know, even satellites don't make a perfect orbit around the Earth, right? You understand? Or the planets even. What happens is that what an atom will do, it goes through shells, but what we're doing, we're talking about the outermost shell of an atom. This is referred to as the valence shell. And what's so important to us is the valence shell determines the conduction characteristics of the atom. Is it a good conductor or is it a bad conductor? Or is it in the center? So what we do when we, so we have individual atoms. This is the smallest particle of any element. And then of course, then we actually, somehow we bond atoms together to form elements, right? You understand that? And the elements are actually listed in the periodic table. So we'll look at different ways that we bond. You may know how atoms bond. Yeah, I know, but they bond in different ways. We have chemical bonds, but we're going to do what they got. We're going to look at what they call covalent bonds, which is one of the primary ways that these atoms. So what we're going to do is we're going to take a semiconductor, which is its atoms that's exactly in the center of being a conductor and being a insulator. A resistor. What's that? No, it's in the center. It's neither a good conductor and it's neither a good insulator. Come on. Semiconductor is right in the center. So what we can do is we can change it by introducing trivalent. These would be atoms that's got three electrons in the valence shell. Pentavalent would be atoms that have 5 electrons in the valence shell. Does that make sense? So semiconductors is going to have 4, guys. So we have two forms. We're going to dope these things to change the conduction characteristics, and then we're going to make one of them have more electrons in the valence shell, and then one we're going to have it have less electrons in the valence shell. This is what we call P and N material. The N material is going to have many what we call free electrons. We're going to dope this with pentavalent donors. the, the P material has many holes. We'll talk about this too as we go along. So we're going to dope these with trivalent electron atoms, also called acceptors. And these two materials are fused together to form a junction that we call a fusion. These junctions are really cool. They're the basis of just about all solid state devices. Fusion junctions. So let's come back and kind of look at this, okay? So here's our big periodic table. Now what we're going to look at is that, and I don't know why this slide's on here. So any material that has between 1 and 3 electrons in the valence shell, we're going to refer to these as conductors. These are going to be classified as conductors. And of course, the ones that have 1 out there, these are the best conductors. Then anything between 5 to 8 in the valence shell, these are going to make good insulators. So this guy that has 4, these are going to be classified as semiconductors. So these are neither classified as insulators or they're neither classified as conductors. But what we can do to these semiconductors is we can deliberately introduce impurities. We call them impurities, but we introduce atoms into the bonding. We either pentavalence or trivalence. So when we look at the periodic table, here's your best conductors right here. In the periodic table, sometimes they show it and sometimes they don't. I don't know if y'all can see it or not. Let's see. Here's the layout of the atoms right here. Here's the layout of the shells. Y'all can't see that, can you? So this says 1 and then 5, and then every one of these, if you look at the first shell, I mean at the valence shell, it always has 1 out there. So that means boron, boron would be a good, insulator. Here's your conductor right here. Sorry. Here's the valence. Here. So here's our conductors right here. So copper has 1, gold has 1, silver has 1, gold has 1, and this guy right here that I can't pronounce has 1. This is a gas, so we don't use that. So here's our primary conductors right there. They all have one electron in the valence. That makes sense? Okay. Here's our insulators. Let's see if I can get it. Let's see if I can bring up a bigger one, guys. Let's go to the internet. See if I can bring up a big one that I can zoom in and out on. That looked good to start off with. That's not going to work because that don't show us the, so these show the layout of the shells. So the first one can have a maximum of 2, the second can have a maximum of 8. What we're doing is we're looking at here that they show no matter how far out it is, it has a maximum of 8. So look at the top right there, right here. At how many? 1. Silver has what? 1. Gold has what? 1. And this guy right here has 1. So here's our basic best conductors right here, right? What are the numbers? These are the electrons in the upper shells. Oh, okay. So this would be shell number 1, right? So shell 1, shell 2, shell 3. This one has shell 4, and this would be out on shell 5. Okay, so what we really want off of the last shell. Okay. That's the valent, called the valent shell. The minimum it can have is at least 1, right? You understand that? And the maximum would be how many? 8. So no matter how far out it is, one of the things that we had to learn when we was in chemistry is the maximum electrons that could be in each shell. But the valence shell always has 2. I'm sorry, at least 1, a minimum, maximum 1, 8. So there's your conductors. Here's your semiconductors. So germanium, silicon, lead, and then this guy down here that I can't pronounce. These would all be what we call semiconductors. Everybody okay? Then up in here, 5, these are 5s, these are 6s. These would be good insulators. Now some of them we're not going to use because we can't use sulfur, right? Because it's a lot, it's a power. So we got to get into things that are actually have shape to them. So we use a lot of compounds, we use a lot like Teflon. We use a lot of Teflon. We use a lot of plastics, thermoplastics, and stuff like that out here. But here's the semiconductors right here. The 2 most widely used is these guys right here, germanium and silicon. We used to use a lot of carbon, but the problem with carbon is it literally is highly affected by heat. And carbon's pretty neat because you can separate it or spread it out, and its opposition goes up, and you can compress it, and its opposition goes down. These used to be the first voltage regulators. They call them carbon power regulators that regulated the output of the generator. So if the output tried to go up, the carbon power would compress. It was made up of a bunch of discs. It would compress, and then that would cause the generator to drop its voltage down. If it tried to open up, then it would come up and add more current to the field. And this is the problem we have, guys. Aluminum, we use this a lot as a conductor, but it's almost a semiconductor. It's got what? 3, yeah. It's not a semiconductor, but it's up on the top end of being a good conductor. So of all the conductors we use, aluminum has the most opposition. But what's the advantage of aluminum? Yeah, it's a lot cheaper than our other conductors, but not only is it cheaper, it's a lot lighter. So we use aluminum to send extremely high powers at extremely high voltage. Y'all know the trick to that, right? Some of y'all should. So what's the formula for power? Yeah, that's the main formula. We have a few, but that's the one we're looking at. So what we're saying is that if I'm trying to sell you power, if I'm not trying to sell you current, and I'm not trying to sell you voltage, then I'm trying to sell you power, which is what the power is work, right? It's electrical work. And I'm not trying to sell you voltage, I'm trying to sell you power. And I'm trying to get that power to your house. So power equals the V times I. So I would be equal to P over V. And the problem is voltage drop is equal to I times R. So every conductor has an R. Now what determines the resistance of a conductor? The size. Okay, the size. The length. We hadn't hit on one of the main ones yet. Temperature, that's the bottom one. Good. 2, 3, 4. Number 1 is the material it's made. Yeah, that's the main guy. The main guy. So, of course, we know that aluminum is used for high voltage, low current things. So what we're saying over here, if I'm trying to sell you power, and I'm trying to sell you that power at about, let's say I'm trying to sell you 1,000 watts, and I do that at 10 volts, then that's going to require 100 amps, right? You understand that? But if I come up here and do that 1,000 watts at 1,000 volts, then I'm going to be able to provide that to you with at 1 amp. Y'all understand that? So the advantage we have with AC is, one thing with AC is we can run it to a transformer and step the voltage up and down. So what I can do with the transformer is I can step up the voltage extremely high to transmit it, right? You understand? And then when I get it down to you, I'm going to start stepping it down for what? Safety. So that's what I was telling people. We're on TVA. TVA, all its power plants are up in the Tennessee Valley, right around the Tennessee River. Bessemer runs off TVA. We're not Alabama Power here. We're TVA. Well, how can they get that power from up in North Alabama all the way down here? Well, they step the voltage what? Yeah, so you think about it. If they step it up to 750,000 volts, they could send 750,000 watts of power with 1 amp, 1 amp of current. So what does that mean now? Well, it means now instead of using copper, they can use what to send it? Aluminum, right? Saves them tons of money, right? You understand? Also, it's a lot lighter, which means the towers that support it don't have to be it's not as heavy as copper, so it's twofold, right? You understand? But the closer we get that down, guys, sooner or later we're going to go back to copper. The closer we get, so when the voltage starts going down, the current is going to have to go up to deliver that power, right? You understand that? So the closer we get to us and the lower the voltage gets, this is why your house is wired with copper. They tried it with aluminum one time. And they burned down a bunch of houses. Well, what got them is not the aluminum. What got them is when they mixed copper and aluminum. So they'd go out to Lowe's, they'd buy the base plugs and they were copper. And then they'd screw the aluminum into it. And then we had, these white guys are dissimilar metals. Dissimilar metals guys will eat each other up. So what would happen, it would oxidize real fast. We're pulling current through resistance, right? It would create heat, and the heat would catch house on fire. So what they do to combine copper with aluminum is they put a paste on it. It's an antioxidant paste that they put on it. So if you go up there where the downdrops from your house is aluminum, if you was to take that off, don't do that, you'd see there's a goop that looks like grease that's wrapped around, that's actually inside the crimp where they go from the aluminum on the power lines over to the copper on your line. So if you've got aluminum in your house, don't go out to Lowe's. You can go out and buy to Lowe's and buy a copper thing, but you better get that paste. They sell the paste out here at Lowe's, antioxidant paste. Or you can buy aluminum outlets. If you buy aluminum outlets, you won't have any problem. So that's why we get by with using aluminum, even though it's got 3 out there in the labor shell. We get by with using it because we step the voltage up so high and the current goes down so low that the voltage drop on the line don't help. So what we do, and I don't know, somehow my PowerPoints are out of whack, guys. So what we do is we take a semiconductor, which has a pretty good deal of resistance in it, right? And in fact, sometimes they use semiconductors as resistors on printed circuit boards, which is pretty neat. And then what we do, and the book does a pretty good job of this, is we'll take it. So what happens is what they're trying to do, to be balanced, what they're trying to do is they're trying to get 8 electrons out in the valence shell, and that's the only one we're interested in. So what these guys will do is they will bond with other atoms that have 4 in the shell. So it creates what we call a crystal. And this would be what we call silicon. So if I had the ability to go out and take a grain of sand and break it all the way down to the atom level, which is basically sand is silicon, and break it down to the area, what we'd see, the way it makes those compounds is it bonds with other atoms. And it forms a lattice. So what would happen is that this guy would have 2, this guy would share 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 2, and what we'd end up with is we would end up with 8 electrons in the outer shell. And this is called covalent bonding. So y'all know the atoms, to make compounds, right? To make elements, we've got to bond, these electrons have got to bond together somehow, right? And one of the main ways is through covalent bonding, where it shares electrons with electrons beside it. This guy right here would come over here and it would have 3 more, and then this right here would be 1 and it would bond there, and this guy right here would bond with around, y'all understand that, and we end up with these things bonded together using what they call covalent bonding. And this is what the atoms try to do. They try to make, when they use covalent bonding, they bond with different types of atoms to try to get 8 out there in that valence shell. And now what's nice with semiconductors, it's real easy to see. So we're not going to have one that's got 2 and one that's got 5, right? You understand, to bond with, and this is what would happen. And then we take elements and combine them with other things to make compounds. So what we do is we deliberately come up here and through diffusion, so we'll take the silicon and they'll put it in a big nice tube. And then what they do is they flow gas through it. They actually gas. And then it's either going to be a pentavalent, pentavalent, which means what? It has 5 in the valence shell. Or they use a trivalent, which has 3. Now what this does is that if it bonds with a trivalent, what this ends up being is instead of having that's okay. Instead of having 8 out here, if it does with a pentavalent, then it's going to end up with 9 electrons in the valence shell. Now this doesn't cause the atom to have a charge because the protons and the neutrons still balance out. The protons and electrons still balance out. But what happens, it puts an electron out there that don't want to be there. So what these electrons do is they bounce, or they automatically start moving, and they start bouncing between these other atoms inside there. And this creates, if it has an extra electron, we refer to this as N material, not because it has an N charge. So to get a charge, to create an ion, what do we have to have? Is we literally got to get rid of an atom. It's got to be gone out of the material. And we can do that. We see it with static electricity. So that's what you're doing with static electricity. Through friction, you're literally making electrons leave that material and go over into another one, right? You understand that? And now if you have more electrons than you have protons, then the material has a charge. So these guys are not charged because these are not leaving the material. So technically, you still have a balance between your protons and the electrons inside the material. So N material is not charged. But what happens is now we have an electron that wants to move around, so we can expose this to an outside DC voltage potential, and the conduction characteristics of it will go up. Because now it's got electrons that it wants to do what? That it wants to get rid of. Right? Does this make sense? Now, if we come over here and put a trivalent in there, then what happens now, instead of having 8 out here bonded together, we're going to have 7. And this creates something we call a hole. In semiconductors, we call it a hole. Because to be balanced, what these things are trying to do on a covalent bond is they're trying to get how many? They're trying to get 8. Well, this guy's only got what? 7. So what it wants to do is it wants to grab another electron. So if another electron is free out there floating around, it's going to grab it and stick it into that absent hole. We call it a hole. So if we dope it with trivalent, we end up with a material that we call a P material. And this is covered in the book real well. So now we got N material. So P material is more conductive. N material is more conductive, right, than regular semiconductors. So they literally do this. But what we get is when we come over here and we bond an N material with a P material. And this little place right here is referred to as a p-n junction. And guys, this is it. This is the way semiconductors operate, with p-n junction. When we deliberately bond those things together. That makes sense? Everybody follow us so far? Huh? We'll get there. Got any questions, ask them. No questions? So what happens is at the instant we come up here and we combine them, we got this guy that's got a bunch of free electrons just floating around. We got this guy that's got a bunch of holes. They're looking for electrons. So what happens instantly, as soon as you bond these things together, then these electrons start migrating over to the P, and then of course they fill the holes inside the P. And what this does, and then eventually this guy gets, so inside this area right here, you have no carriers. You have nothing to carry current. We call them majority carriers. So inside the P region, so this is the P, then the majority carriers is what we call holes. These are holes. And what is a hole? It's the absence of an electron in the covalent bond, right? You understand that? This over here, the majority carriers, is electrons. So what happens as soon as we bond this together, then what is going to happen is we're going to have some electrons that moves over into the P material and fill these holes. Right, understand? And then what happens is they move over, then we end up with no majority carriers inside here. And when the length of this gets, the width gets so high, everything just stops.
What's that space?
It's called a depletion region. Because there's no majority carriers within the depletion region.
So how do we know what we have? Depletion region and end junction?
It's not, it's in between, it's at the junction. The depletion region is at the junction.
Okay.
So what we end up, guys, is now we end up with the P material has too many electrons and the N material has too many holes. So, I mean, it has holes now in it, right? You understand that? And what happens, it builds up a difference in potential. So it actually has a difference in potential that we can measure. You can't measure it on that, but so it doesn't support a lot of current. It doesn't support a lot of current. So you can't get a load out of this difference of potential. So what we can do is we used to check these things with an ohm meter. Because what you would find out is that one way it would have a real high resistance because everybody knows an ohm meter is actually a source, right? You understand that. And what you're doing is most of your ohm meters now are what we call constant current sources. So when you come over here, so your ohm meter is one of these, but instead of being a voltage source, it's a constant current source. So that means if this guy puts out 10 milliamps maximum, then what we can do is that what the meter does is it automatically raises its voltage up to put out 10 milliamps and through resistance. And 10 milliamps means it can display that up there, turn on a dot somewhere and put ohms over here, right? You understand that? And this is why if you put an ohm meter into a circuit, a live circuit, you can damage your meter because you're going to be pushing current back through your source, right? So be real careful on that. But the problem is that when we use an ohm meter, so I'll show y'all this. What we end up with this thing is we end up with, let me see if I got my camera running. Okay. I don't see it. So we end up a thing, it's going to be usually in, some of them's in plastic. I'll show y'all some, that's not going to do it, so let me just, that's that one. I'll probably have to just pass this around to y'all. I had my camera with me this morning, so I'm not working now. What you'll see, it's got two leads. And then it's got a stripe on one of the leads. Yeah, this is identifying the end side. And then this right here is the one without the stripe is identified as the P side. Yeah, these guys are called diodes. It's called a diode. You need to make it plural. Oops. There we go. By the way, the 5-volt supply is bad on this thing. So one of the things we'll do, you see the light blinking? One of the things we'll do is we're going to fix this thing. I'm going to come over and put my meter on. I think 10 meg. And by the way, you don't need, when you get up here, guys, y'all don't need to touch the meter lead, right? Because what it's going to do is going to do what? It's going to measure you, right? So what I'm going to do is I'm going to come over here and I'm going to take the black lead and put it toward the stripe. And then I'm going to come over here and touch the other one. And notice it's measuring 1.4 megohms, right? See that? And then we'll come over and put this around. And I'm going to measure overload. So what we're doing now here is we're working against the barrier voltage. Here we're working with it. Make sense? Yeah, to see it actually work. Now, what they did is, remember, and this is the way we would check these diodes to see if they're good. So what we're trying to do is we're trying to look at a real high ratio between this way. So this is infinity, right? Understand? Let me get my fingers off of it. This is the highest. There's really no such thing. We call this infinity, but there's really no such thing as infinity, right? It's just that it's got a resistance so high that I can't measure it. And then when I take this is the negative lead of your of your ohm meter. And I come over here and put it this way, then it measures relatively, it's still megohms, guys, but it's, so what we're doing is we're actually looking at an indication of that voltage that's being produced. Now this became very confusing, especially trying to figure out what size. So what they did is they came up with a scale on the meter where it actually shows you the voltage that's required to cause this thing to work. And it's called this guy right here. So this is the actual symbol of a diode, guys. Can y'all see what it looks like? Now, I'll draw it in a minute. So I'm going to come over and put my meter on this diode scale. And now when I come up here and measure this, oops. I did it then. There we go. Now notice what it changes to over here. It changes to what? Millivolts. I'm going to come and measure this now. And so it's measuring about 600 millivolts. And then I come up here and hook it up. So that would be this direction right here. With my black lead toward that stripe, and then my red lead on the other side. And then this meter don't show overload on this, by the way, but notice here it's not going to change. So your meter will probably show an overload. So what we're actually doing now on the diode scale is we can actually see that barrier that forms that, because now when they migrate over, we're forming ions, right? Understand? So now we have a difference in potential, and we're actually able to measure that. But you can only measure it if your meter is on what scale? Yeah, we call it the diode scale right here. Actually, it's the p-n junction scale, but they use the symbol for a diode. So we can use this to check any device that has a p-n junction in it, which is pretty neat. So the barrier potential, this is the presence of positive, negative ions on the opposite side of the transition region. The barrier voltage, we can look this up on data sheet. So every solid state device has what we call a data sheet. But that gives you the maximum current it can handle, the maximum voltage it can handle. It also gives you the barrier voltage. They refer to this as VL.
Says AF.
That's average, it's an average. If the amount of voltage necessary to move electrons through the electric field formed by the junction. So what we're saying is that if I come over here and I have this thing, and this is the symbol, guys. So here's the symbol. This should be colored in, but it takes a little while. So a lot of people don't color that in. And then I put a bar. So what that is, this is indicating the N side, and then this right here would be indicating the P side. So then the actual device itself, yours is, I passed around was black, so mine's going to be opposite. We have that line that goes around here, and so this lead right here would be the N side, this lead right here would be the P side. Now what we're trying to do is we're trying to push current back through the barrier voltage, right? You understand that? And of course what would happen, if I come over here, and as soon as I come over here and exceed this voltage, so if I was to come over here and put 1 volt, then this barrier voltage is going to block this. But as soon as I exceed this, then the current flow is going to flow through that thing, right? That makes sense, right? So that's what we're measuring. We're measuring the amount of current, the amount of voltage that's required to cause this depletion region to block. What's going to happen? Let me go back to my blank slide. I didn't say right here. I lost my drawing utensils down here. There we go. I lost it again. I know what's going on. So if we're on the N material, we got a bunch of free electrons. So let's just come over here with minus. And then over here we got a bunch of free Hubble's. So we're just going to come over and represent those as pluses. As soon as I bond that, what we end up with is we end up with a depletion region. So now we end up with ions, right? You understand that? So what we end up with is we end up with a little barrier voltage that's sitting in here like this. So what happens if I come over here now and I put an N right there, a minus on my power supply right there, and I come over here and put a plus, what's the plus going to do with the pluses? What does like signs do? They repel. So that's going to start pushing these guys into the depletion region. This is going to come over here and start pushing this minus is going to start pushing these into here. And what's going to happen eventually, the depletion region is going to collapse once we exceed whatever that voltage is right there. And now this sucker runs wide open. So now these guys, as soon as that collapses, we're going to have all types of, these guys are just going to start pushing in. They're going to start combining in the center, and we're going to have current flow. What's really interesting in semiconductors is that we have current flow, 2 different types of current flow. So normally outside the semiconductor, we say it's electron flow. Inside the semiconductor, we have both hole flow and we have both electron flow inside the semiconductor. And this is something you'll have to get used to. And what happens is these guys are pushing up against the depletion region. And what's going to happen eventually is if we get the voltage up high enough, what is it going to do? It's going to break through, right? Does that make sense? And all of a sudden we have conduction. And now it's going to act a lot like a conductor. It's not going to be a semi. It actually acts like a conductor now. So what happens is these combine in the center. This guy keeps pumping electrons in on this side. This guy keeps pumping in holes on that side. And this guy now all of a sudden just avalanches. As soon as we exceed this voltage right there, which we call the barrier voltage. For silicon, different books teach different things. Our books teach is approximately 7/10 of a volt for silicon, doped silicon, and approximately 3/10 of a volt for germanium. And these are the two most popular used semiconductors. Now LEDs, they use gallium. They use gallium, doped gallium to make them work. And they have a real high VF. So most LEDs, if you forward bias them, they're going to drop around 2 volts. Because they're not in there they're in there to create light, right? So LEDs, light emitting diodes, those are, they have basically the same symbol. We're going to study LEDs in this class. But what we do is we come over here and we put arrows coming out of them, and that indicates light. Now what happens if I was to come over here and put the opposite polarity on this thing? Don't mind doing what it is. I have to do this. Got my depletion region. What happens when I come over here and put a negative right there and I put a positive right there? What this is going to do, this is going to attract holes out of here. This is going to attract electrons over there, which makes the depletion region get bigger. So what happens when we reverse the polarity, this guy becomes basically an open. An open, yeah, because the depletion region comes out. As long as we don't exceed, there is a path through there, guys. So as long as we don't exceed what they call a breakover voltage, we're okay. So sooner or later, you got enough voltage, you can push current through anything. And if we push current through that, depletion region, right, when it's real big, it's dropping a lot of voltage and it literally burns the diode up. So every diode is going to have a voltage. We call it the breakover voltage, peak inverse voltage, which is the maximum voltage you can put across this thing to cause it to blow off, which is pretty cool. So these guys are our check valves. What's the check valve? Yeah, it only allows flow in one direction. These guys is what does that. So if I was to come over here and do this, let me find my blank slide. There it is. I keep advancing it. So what I'm going to do is I'm going to choose a DC source, is what we'll start off with. And then I'm going to come over here and I'm going to put a diode. And notice I'm putting the P side toward it. And I'm going to come over here and I'm going to put a resistor right here. And let's say we'll make this 10 volts. And we'll make this 10K. So what's going to happen is this guy right here is going to, this is going to pull the holes out of this and make the barrier region bigger. This is going to pull the electrons out and make the barrier region bigger. So what would you expect if I put a voltmeter right there? What would you expect to measure? And then I put a voltmeter across the diode. What we use the definition. I'll take a guess. This is no. We're just measuring volts. No, we're gonna get 0 volts right here, and we're gonna get 10 volts right there. The diode is set up to block. If I was to come up here, but that's a good guess. I mean, it's so basically what we're doing with our diode, guys, is we're doing this. So when we put the P right here, and this is the symbol. So when we put the P toward the P and the N toward the, we put the, if we put the, I'm wrong. Right. Yeah, you're right. Good gracious, guys. I'm going to delete that off the record. So, you know what we say, right? I was just seeing if y'all paying attention. Oh, I love it. That's embarrassing. I know it. Thank you. Yeah, I'm gonna edit that report. I'm looking for my blank page, guys. Let's make it a 1K because it's like, so what I like about a 1K is it's 1 milliamp per volt, right? So we put the P on the side, pushing the P toward the center, right? And we're putting the N on this side, which is pushing toward the center. So what that's going to do is going to come over here and basically do this. This is going to close the switch. But we got to remember something. If this is a 1K, what voltage drop would, I need to turn off mine. If this is a 1K, we got plus here and minus here. How much voltage would we measure across the 1K? Huh? Close. We'd measure about 9.3. Yeah, because it's 7/10 right there. So it's not a closed switch. We say, and by the way, we call this, when we put the positive toward the P and we put the negative toward the N, positive toward the P and the negative toward the N, we refer to this as forward bias. Now bias, these are DC voltages. Applied to a semiconductor. We call them semiconductors, but actually they're not semiconductors anymore, but we still call them that because as soon as we dope them, they change their characteristics, right? I'm going to have to turn off my touch screen. Every time I touch it with my fingers, it's causing problems. It's hard to write out in space. So bias, these are going to be DC voltages that we apply to semiconductors that control their conduction characteristics. So when we put the positive toward the P and the negative toward the N, we call this forward bias. When a semiconductor is forward biased, it's gonna act like a closed switch, right? But it's not a closed switch because we have to consider that barrier voltage. Now, if I was to come up here and do this right, well, let me erase it. If I was to come over here and do this right, no, well, we could do that. Let's just change the power supply. So I guess it would be, I can't erase, guys. Let's just redraw it. So what we're going to do now is we're going to come over here and point the negative toward, I'm not going to color that in here. And instead of drawing that wire, we'll draw a common. So what would happen now is over here, if this was 10 volts, over here I would measure 0 volts. And then across the diode, I would measure 10 volts. So now it's acting like a wall. Yeah, it's acting like an open switch. I got to turn off my touch screen. Can y'all see what's going on? Yeah, every time my fingers touch the thing, huh? Yeah, let's go ahead and take a break while I set this thing up. 10 minutes, right? Sounds like a good opportunity.